Okay. Take it away.
Can you see my slides? Okay, so hello everyone. I'm Yu-Ching Chen, and you can also call me Tony. And I'm a fourth year graduate student in University of Illinois. So today I'm happy to share with you our new discovery, which is the periodic quasars from Dark Energy Survey plus the Sloan Digital Sky Survey. And I will also talk about their implication on LSST. And this is a project from a large collaboration from several people in UIUC and also the Dark Energy Survey collaboration. Okay, so first I want to make a brief introduction. So as we all know, like from the observational evidence, most of the nearby galaxy, they harbor a supermassive black hole at their center. And from the simulation, we also see the hierarchical merging galaxy. So combine those two factors, we should expect to see the binary supermassive black hole in our universe. However, searching for those binary supermassive black hole is very hard. And understand those binary supermassive black hole can help us to solve several problems, such as the final parsec problems, and understand their redshift dependence, and know the demography of those binary black holes. However, as however, the separation of those binary supermassive black hole are very small. So even with the VOBI, the very long baseline interferometers in radio, we cannot resolve them. So we need to rely on several indirect methods. For example, the periodic signal in the light curve we have seen in the previous talks, either due to the Doppler boosting, which is like the simple sinusoidal, and or due to like more complicated accretion models such as the hydrodynamic modulation from the black holes. Or we can use the SED of those binary black hole system. So if there is like the binary form a 2 mini disk and also a large circumbinary disk, there will be a gap between those mini disk and the circumbinary disk. And those gaps will contribute a deficit in their UV or to optical SED. On the other hand, we can also search for the radial velocity shift in their broadline region. So by measuring their broad emission line, we can know if there is a black hole, the binary black hole orbiting around each others, and we can measure their radial velocity shift and understand if it's a possible candidate. And in the following talks, I will focus on the periodic signal in light curves, especially those from the Dark Energy Survey and the Sloan Digital Sky Survey. So in order to make a long enough light curves, we combine two surveys. One is the Dark Energy Survey. So Dark Energy Survey is a 6-year multi-band GRIZ imaging surveys starting from 2013, and it used the Blanco 4-meter telescope in Chile, and it has a very large field of view of 3 square degrees, so it can image the whole sky very quickly. And the DES consists of 2 surveys. One is the wide field survey, and the other one is the high cadence called supernova survey. So we mainly use the supernova survey to form our light curves. And the data, the cadence in the supernova fields is around like 1 week, 6 days. So which is very good for composed light curves. And the typical single epoch depth of the DS is around R band to 24, so which is very deep compared with other surveys. And there is a 4.6 square degree overlapping region between the dark energy survey supernova fields and the Sloan Digital Sky Survey Stripe 82. So we used the data sample in this small region, trying to search if there is a possible periodic quasar, which might be a possible supermassive binary black holes. So we start with the spectroscopically confirmed quasars in this region, and we also require like they should have the sufficient epochs and also use like some quality flags to ensure they are artifact free. So our final sample has around 625 quasars, and there's redshift distribution and the magnitude distribution are shown in the right hand side. So as you can see, for most of our quasar sample, they are at high redshift. The median redshift is around zero point 0.8, and they are quite faint. They can the magnitude limit can reach around like R-band 223. So we can prop the different population like high redshift and the faint population compare with other surveys. So here I'm showing you a composed light curve for one of our candidates. So on the left-hand side is the SDSS light curve and with the multi-band light curves. And on the right-hand side is the dark energy survey light curves. And as you can see, the photometry uncertainty in the dark energy survey is very small compared with the Sloan Digital Sky survey. So this high quality light curve is very essential to search those periodic signal as well as understand their origin. So how do we select those periodic quasar candidates? We mainly use the generalized Lumsgargo periodogram. So the generalized Lumsgargo periodogram is a periodic search algorithm to find like mainly used on the uneven sample data. So in order, however, the quasars also have their own intrinsic variability. So we cannot ignore them and just use the periodogram. So we compare our quasars with the Mach quasars fitted in using the DRW models. So the DRW model is uh, a good model to model the quasar's variability. So if the peak of our quasars in the periodogram is higher than certain point that in our criteria is 99.74% in at least two band, which means like the periodicity we have seen uh, for these quasars are deviate from the typical DRW models, which means it might be a real sinusoidal or like periodic signal. And we also add like some other criteria such as like the signal to noise ratio larger than one, and we also check they are consistent with the autocorrelation function. So we have found 5 strong candidates out of 600 quasars, and because we have the significant level from the DRW, so we can also estimate it, like how many of our candidates are due to like the noise or the limited sampling. So we can calculate the false alarm probability, and we find like up to 1/3 is of our candidates might be the false positives. So it's around like 2 objects, and we are not just seeing the noise from the DRW. And because like our candidates, they are all spectroscopy confirmed, so we can use their single epoch their emission line to estimate their black hole mass, and they are around like 10 to the 8.5 to 10 to the 9 solar mass. And if they are binary, so their gravitational wave in spiral times are around 10 to the 4 and 10 to the 5 year, and the separation is around 4 to 6 milliparsec, which is very small. So we can even resolve them in the VLBI. Because the dark energy survey and the SDSS, they are multi-band imaging surveys. So we can test the Doppler boosting hypothesis. So if the periodicity we have seen is mainly due to the circular orbit of two black holes. So the Doppler boost hypothesis, it predicts the amplitude is correlated with the spectral index in each band. So we can use our data to test if the amplitude is deviate from the prediction. So on the right, those color data are from our data. The color points are from our data, and the black line are from the prediction from the Doppler boosting. So we have found like most of our candidates, they are deviate from the theoretical prediction of the Doppler boosting, which might suggest that the periodicity we think is more maybe from the more complicated um, mechanisms, not just like the simple sinusoidal the signal from the Doppler boosting. And we can also compare with previous studies from the Catalina and PDF, as well as the Penn stars, and we find like our detection rate is slightly higher than those previous studies. However, like different study, they have different selection criteria and data quality. So it's not a fair comparison to just compare like how many of like the detection rate. So, but we believe like the longer time baseline is essential. The longer time baseline and the better sensitivity are essential to to search those periodic quasar candidates. And on the right, I'm showing the comparison of our candidates with those in the magnitude and the black hole mass, as well as the redshift. So as you can see, our candidates prop a different region in this magnitude redshift plot. And because like our quasars are at like higher redshift, around redshift 2, so this in the redshift 2, we usually call it like the cosmic high noon, which the quasar activity peak. So we should expect to see maybe more like uh, periodic quasars or like the binary supermassive black hole at this region. And we are hoping to, so for the LSST, we with the like more better sensitivity, we believe we can find more and more periodic quasar candidates in this region, as well as at higher redshift. However, we cannot just direct link the periodic quasars with the supermassive binary black hole. We should still like understand other physical interpretations. So we discussed like few other physical interpretation for our candidates. So first is the processing radio jets. However, our candidates, they are not blazars, or their optical emission is not dominant from a radio jet. And we also have like some follow-up uh, radio emission from VOA, and we find out like 3 of our candidates, they are radio quiet, so which will the processing radio jet is highly unlikely to contribute to this large optical amplitude. As for other interpretations, such as the tilted accretion disk, the amount of the obscure continuous emission will be too large to explain the observed variability amplitude we have seen. But there are still a possibility of the QPO. So there is the timescale of our candidates is broadly consistent with the scale up Adrian version of QPO. So we still need the continual monitoring of our candidates because some the QPO will show the drift in their amplitude and the phase. So we might see like the different amplitude and the phase shift in the future light curve if they are QPO.
You have 3 minutes left.
Okay, great. Thanks. So because like this meeting is focused on the LSST, so I would like to make like some implication on the LSST. So speaking of detecting the periodic quasars in short term, so in the first few years, LSST will be a like very great uh, follow up for those currently found periodic quasar candidates is around like 200 periodic quasars from either the Catalina, PTF, Penn or even from our study. And it will help us to reject or confirm their periodicity. Also, like for our periodic quasars, we focus on like the yearly periodicity. However, with the high cadence or the deep drilling fields, we might be able to probe a more shorter periods around like weekly periods. And we are hoping maybe it will be a good, although we expect to see fewer candidates in the shorter periods, but it's still it's good to try it. And in long term, like if we have the full 10 years light curves, we we can calculate like maybe how many periodic quasar with period around years we can find. So assume using a very conservative 0.1 percent detection rate, and with maybe 10 million quasars in LSST, we might find like order of 10,000 of periodic quasars in LSST. So those 10,000 periodic quasars might help us to study the demography of the periodic quasars if they are from the binary black holes or they are from QPO or other physical interpretations. And we can also add this good data set with some existing imaging surveys like ZTF or DES, and we can form a longer, like decade-long light curve to search the long-term variability. And speaking of the origin of the periodicity, so because the LSST will give us a very high quality light curves, so we can use this precise shape of the light curve to determine the origin of the periodicity. If it is just sinusoidal or is more bursty, so those the shape of the light curve is very essential. And as I have shown, like the multi-band light curve can be used to test the Doppler boosting hypothesis, and LSST will be very good at it. And of course, we can also combine with other multi-band, multi-wavelength survey, such as the VLAS in radio or Euclid. So for example, like we can cross match with the VLAS and to determine their radio loudness and trying to know if they are radio quiet or radio loud and use it to reject or confirm other physical interpretations. Of course, we can also, besides the binary supermassive black hole, we might also discover a new periodic transient. For example, the the repeated partial PD in the Penn et al. 2021. So they use like the test and also assassin to discover this kind of repeated partial PD. So we might also see this new periodic transient in LSST. And I think I will stop here and take any questions.
Thank you very much. I see that there is a very lively discussion on the chat already. There's a number of questions. So we're running a little bit late, but I think we have time for a question if anybody wants to ask. I mean, I don't know if Ilsan, if you want to mention what you've been putting on the chat.
No, not really. Basically, I was just curious, but the provided answers perfectly make sense to me. But the LSST area, we might be able to do some detailed modeling.
Perfect. And Tony, I don't know if you have had a quick time to scan the chat, if you want to add anything to those answers.
Yeah, so I was just looking at the chat. Oh, yeah, so speaking of I see Luke asking like how's the up to 1/3 of false positive. So yeah, so we can like, let me go back to this. So for example, we can calculate like using those Lie curve to determine like how many of them are above like the 99.74 criterion. So we can calculate how many of those Mach quasars they are above this criterion. So which is the same as our criteria. So use those, we can derive the false learn probability. So yes, and we also used other selection criteria to test those Lie curve. So the final like up to 1/3 of those is from the method we use. Does that answer your question?
Yes, thank you.
And let me see. Are those data is from Michael? Are those data consistent with the constant color as the quasars vary? Yes. So yeah, because we only have let's see.
Oh, if you want to take a time to actually read them, you can post the answers.
Okay, sure. Yeah. Of course, if we are running out of time, we can just move on.
I think we have 1 minute before we have to move, and I see a new question. So Maria Carisi says, would your sample be consistent with the gravitational wave background limits, especially since you find higher rate than CRTS PTF?
That's a good question. So we haven't thought about that. So yeah, we haven't compared like our sample statistic with the gravitational background, and I think that will be a good good thing to do in the future. Yeah, so yeah, thanks for that. We haven't thought about it.
No, actually, it's consistent. We have calculated that. The main reason that it's consistent is because of our survey, which is small pencil beam survey, basically, which is deep and most sensitive to the less massive populations at high redshift. So it's not the populations that are PTA sources, because the PTA sources, they are dominated by the most massive populations and at low redshift. So we don't actually have a constraint that would be directly relevant for PTA. So if you look at our sources, we actually fall in between the PTA and the LISA sources.
Mm-hmm.
Well, thank you very much. I think we have to move on to the next talk. So, but we can save the questions for the discussion session and also keep posting things on Slack if you want to put them up for the discussion. So thank you very much. And let's move to the next talk by Colin Burke on interpreting the characteristic timescale in AGN light curves, implications for Rubin Observatory.
Okay, hopefully that shows up okay.
Yes. Yeah, looks good.
All right, thank you. Thanks to the organizers. Yeah, so today I'd like to talk about our work on the characteristic timescale of AGN light curves. And so I'm also a graduate student at Illinois, and I'd also like to acknowledge my collaborators, especially Xin Liu and Yu-Ching Chen, who I've been working with on this work. And many of them, a few of them are here in attendance, so hopefully we can have a good discussion. So yeah, I don't need to explain to this audience that AGN variability, of course, is stochastic, but the interesting question that we're trying to address here is how can we interpret the variability of the light curves, and can the AGN variability parameters be related to the physical qualities or the physical parameters of the accretion disk. So generally speaking, AGN variability, AGN light curves are well described by the damped random walk model. Although deviations from the damped random walk do exist, which I'll maybe touch on a little bit later, that really doesn't affect the fact that we have this characteristic damping in the light curve, where at least it's a general property that you have red noise on short time scales, and eventually the light curve power spectrum flattens low frequencies on longer time scales. And so that gives the sort of characteristic variability that we see in AGN light curves, where they're approximately stationary over long observational periods. And so this bend in the PSD corresponds to a characteristic frequency or time scale. And so I'm really interested in what this time scale can teach us about the accretion physics and the AGN accretion disk system, since we believe that the AGN variability primarily comes from the accretion disk. So there are difficulties with measuring this break time scale, which are very, very important. One is that the light curve, at least with simple damped random walk modeling, the light curve must be of sufficient length, roughly 10 times the length of that time scale, or tau, as I'll refer to it as tau in my talk. And then the light curve must be well sampled enough. So if you're trying to measure a time scale of 100 days, you need a cadence or sampling of at least 100 days or better in order to measure that. And then also very important is the light curve must be of sufficient quality, and that basically means the signal to noise or the amplitude of the variability should be sufficient that the damped random walk model is reliable. So you can fit a damped random walk to anything, pure noise, and you'll get a result, but we tried to be careful and make sure that our damped random walk modeling is reliable by imposing these constraints on all of our light curves before we do this DRW modeling. So here's an example of a light curve, which is work I did about a year ago using TESS. And so the great thing about TESS is the cadence is really, really rapid, as you can see from the light curve here. So the left is, the right figure here is the light curve. And so this is a dwarf AGN called NGC 4395. And I wanted to look at NGC 4395 for a couple different reasons. One is it's a famous AGN, dwarf AGN, with one of the smallest supermassive black holes that's known, at least nearby. It's also very bright, so TESS unfortunately can't look to very faint depths. So the fact that 4395 is very bright, And it's also known to have very rapid and high amplitude variability, at least anecdotally, because it's such a well-studied galaxy. So I thought this would be a perfect target for tests. And indeed, we saw quite a beautiful light curve using tests. And after detrending the light curve, which I won't go into the details of that for this talk, we were able to extract a damping timescale of 2 to 4 days, which is roughly consistent with what we would expect from the timescale mass relation from previous work by Kelly et al. 2009. So they studied a range of AGNs and did a similar analysis. And so our data point here with 4395 with black hole mass of just roughly 10 to the 5 solar masses, I was happy to see was almost exactly as we would expect from the previous work over 10 years ago. But the uncertainty in this relation, especially at the low mass end, is quite large, as you can see. And some of that is due to the limited dynamic range of the sample from 10 to the 8 to roughly 10 to the 9 solar masses and black hole mass. So we said, well, we should try to fill in this relation across the full range of supermassive black holes and see if this relation one holds, whether it's actually there, after being careful about the light curve length and modeling, et cetera, and if we can improve the relation, if it indeed is there. So to do this, we collected a sample of light curves from published public data in the literature. One of our primary sample, most of our objects are 20-year-long light curves from a variety of surveys going back to SDSS, and including, importantly, the dark energy survey supernova fields, which are higher cadence fields, which were monitored with a cadence of about a week. So that really helps constrain the variability on shorter timescales, and the 20-year length allows us to have a long enough duration to measure this timescale, even for massive quasars. And so all of our sample as well have a broadline black hole masses and spectra. We have supplemented this with reverberation mapping, individual reverberation mapping light curves, and dwarf AGNs from the literature using ZTF. And since we would expect dwarf AGNs to have a more rapid variability, as the NGC 4395 example, thankfully for these sources, we don't need a 20-year-long light curve. Only a few years is good enough. And so this sort of orange error ellipse model here is our damped random walk model, an example. And so the nice thing about this sort of Gaussian process fitting is it doesn't really matter if the sampling is irregular. It can sort of handle that consistently. And we did a lot of simulations to double check that as well. So that's the strength of the Gaussian process fitting. So in the end, we have roughly 60 light curves out of our parent sample of 400 that met the duration and quality constraints. And so I'll talk about LSST at the end, and this is really going to help us get even longer light curves in these fields, which will continue to be monitored by Rubin. So this is a result that's in press in Science, where we showed our new relation using the updated data sample. So our data points from optical light curves are here in black. So NGC 4395, same as before. So dwarf AGNs, typical Seyfert galaxies, and the SDSS quasars. And they follow nicely with this correlation across the full range of supermassive black hole masses. And what's interesting is, as you can see, compared to the X-ray data in red, the damping timescale is longer, the optical, and the slope is also very different, much more shallow than the X-ray relation, which is quite interesting. So we think that the X-ray relation traces the ISCO radius for various reasons. And the question is, how can we interpret the shallower optical slope? So the fact that the slope is so different, we think rules out simple origins of the optical variability, such as X-ray reprocessing or other extrinsic processes like microlensing. And we think this is intrinsic process in the accretion disk. But to interpret this break timescale relation a little bit further, we can compare to, we can sort of transform this into the characteristic timescale, damping timescale into a characteristic radius. And when we do that and scale it using the known wavelength scaling of tau from previous work to the UV radius, we find that our result here in the orange is consistent with the microlensing results from Morgan et al. 2018, microlensing observations of accretion disk radii at 25,000 angstroms. So that's the blue here. And if we assume that this radius is indeed the UV radius, characteristic radius, then that implies that the characteristic timescale we're looking at is the thermal time at the UV emitting radius. And so that, but it implies that alpha, which is the viscosity parameter in the standard Shakura-Syneev accretion disk model, is pretty high, around 0.05. So here we're showing the thermal time with alpha of 0.01 and compared to the orbital time and the dynamical time. So they all scale roughly the same with this sort of Keplerian radius, but there's different factors of the viscosity parameter alpha or 2 pi, whether it's the orbital or dynamical time. So that's why these are all, the normalization is different for these various time scales. And ours is more consistent with the thermal time scale, but with an alpha of roughly 0.05. Okay. So then we thought, well, what happens if we extend this to stellar mass accreting systems? So we added white dwarfs from a previous study, Scaringhi et al. 2015, which have very rapid variability in the optical, as we would expect. And we find that they are roughly consistent with our relation in the orange again, within about 2 sigma. And they're consistent with a fixed slope of 1/2, which I'll talk about, mention why that might be in here in a moment. But what's exciting is that this, if it holds, indicates that there might be some universal relation between the optical characteristic timescale and the mass of the white dwarf or the central compact object for all accretion disk systems, at least that are rapidly accreting. And so this, and you'll notice there's a gap in between these. And so this is what I'm particularly interested in, which is the intermediate mass black hole range here in the middle. So we have yet to find really a good example of an accreting intermediate mass black hole. And our hope is this timescale mass relation could perhaps be used to predict what a accreting INBH light curve might look like. So just for fun, we also plotted all of this on sort of the same plot to try to unify our interpretation of this damping time scale. So here I plotted the damping time scale versus the orbital time. And so the y equals x line here is the orbital time. And for comparison, we have the thermal time with our value of alpha of 0.05 and 0.01 as well to guide the eye. So the black data here is our optical AGN timescales, and the red points here are the X-ray break timescales. And we also show the white dwarfs in the optical. and stellar mass black holes as well, measured from X-ray light curves. And so our optical relation appears consistent with the thermal timescale at alpha of 0.05, and the X-ray could be consistent with that. It could be, the scatter is larger. It could also be consistent with the orbital time at the ISCO radius, which explains why the slopes would be different in the X-ray and optical, we think. So since this conference is related to Rubin Observatory, I'd like to now go into the final part of my talk, which is what we think are
you have 3 minutes left.
Perfect, 3 minutes. Excellent. So we'd like to talk about the implications for LSST. So in summary, we think we built a timescale mass relation to estimate the mass of the black hole in AGNs, provided the length and quality are sufficient. So the real benefit here of LSST will be the longer light curves will allow us to add more data points for the more massive quasars, which have longer characteristic timescales, and you need a longer light curve in order to measure it reliably. So that will allow us to perhaps reduce some of the bias in this relation. By imposing this duration constraint, we've imposed a slight selection effect on our sample. So LSST will hopefully allow us to reduce that by keeping those more massive quasars into our sample. And that we think could steepen the slope a little more to be more consistent with a slope of 1/2, which is the prediction from the standard accretion disk model. We are continuing to monitor the supernova fields before LSST begins. So we'll have great continuous light curves for at least 30 years, high quality photometry for all of these objects, at least in our 20-year-long sample. And it can also help address the uncertainty in the relation, and we'll see if we can really constrain the viscosity parameter alpha maybe a little bit better. In addition to perhaps using this to discover intermediate mass black holes. So this is one of the most exciting, I think, outcomes of our relation here is if you extrapolate it to the low mass end, can we use this to look for particularly to target light curves with rapid variability on the timescale of hours to days. And the standard Rubin cadence won't probably be good enough to have a high enough cadence to measure a timescale on the timescale of a few days or hours. But it's potentially an opportunity to piggyback on, say, a high cadence mini survey. So here's just a simulated light curve of what an intermediate mass black hole might look like. And the nice thing is you don't need a really long light curve, you need a high cadence. So it comes with its benefits and drawbacks. And we think we can look at low mass dwarf galaxies, perhaps, which may host active intermediate mass black holes. And it's also interesting to look at the demographics of those, which is a way to distinguish between different seeding mechanisms at high redshifts. So I think I'll end it there and happy to take any questions. Thanks.
Thank you very much, Colin. I see that there's a question in the chat from Ilsan. I don't know if you want to ask it now.
Yeah, okay, so I just read it. Sorry if I missed the part of your talk, but I was basically wondering, how do you measure the error of your tau realistically? Then to discriminate between different alpha disk scenario, how much accuracy do you need? And will LSST provide the sufficient data to measure with that target accuracy?
Yeah, great question. So on the individual data points, you can measure tau more accurately if you have a longer light curve. So we just used the standard Markov chain Monte Carlo fitting and sampling of the posterior to estimate the errors on tau. And we also double checked with simulations by varying tau and varying the light curve lengths and seeing if we can recover the tau with the right errors given the quality constraints on the light curve. So that was kind of the motivation for our quality criteria, is if tau can be reliably recovered from the light curves. So that's why we restricted our sample to only good light curves, which really helps with that. And so to answer the second part of your question with LSST, I think the main power will be the individual data points on those quasars will get smaller. So we could perhaps look for deviations there. And we could also increase the sample size throughout the full 10-year survey. If we have some spectroscopic sample, we'd have more objects that we can have LSST light curves for. But it's also there's some intrinsic scatter in the black hole mass, which could perhaps limit how good we can get. But yeah, very good question.
Mauricio?
Thanks, Colin. Very nice talk. I have two questions. The first is you showed that your model disfavors the reprocessing of X-rays to produce the optical variability. But in part, we know that some reprocessing occurs anyway. So I was wondering if this is mainly due to the fact that short time scale fluctuation are not accounted properly in the long light curve that you have. And the second one was just trying to understand, you presented this plot that you're showing here, and then at the end you put X-rays and optical together. I didn't understand how that worked.
Sure, yeah, so to answer the first question, yes, I think you're right. On very short timescales, there probably is some X-ray reprocessing, but we think that wouldn't affect the timescales on days and years that we're measuring here. So you're right, there probably is some component of X-ray reprocessing, but we don't think it's responsible for the typical optical timescales and optical light curves at least on these timescales that we would see certainly with Rubin. To explain this plot a little more, so what we did is we just computed the orbital time using the characteristic timescale. So the reason they're on the same, it's sort of confusing. So here tau is on the y-axis. So the X-ray taus are still much shorter, but because we think the orbital time for the X-rays scales linearly with the mass, if it traces the ISCO, and the optical scales differently with the mass. So if we incorporate that scaling, then those different scalings, then we can plot it on the same graph. I hope I explained that okay. And if UA is in the audience, perhaps he could chime in. But.
Yeah, I was just typing in the chat window, but that's probably easier to speak up.
Yep.
Basically, the orbital timescales are estimated at different radii. In the Asian population for the X-rays, they're coming from much closer. That's why their timescales are much shorter. But for the same population of AGN, the optical emission comes from the accretion disk, which are more extended. So that's why you have a different time scale, which is tracing the damping in the accretion disk variability. That's why you can put those points in the same plot, but the measurements for the damping time scale for the X-ray data comes from other people's work.
Yeah.
Thank you.
Thanks.
Thanks. So we have time for a very quick question. I don't know if your question is quick, Luke.
Yeah, I think so. So if the variability or the damping timescale is associated with the thermal timescale, then there should also be variations with Eddington factor. Have you checked that?
Yes, so we think our sample of AGNs, we have the Eddington luminosity ratios collected from the literature for most of them. The dispersion in the Eddington ratio is not that large. So we don't think it would really change the damping timescale. So we don't find any significant trend in our sample with say, the mass and the Eddington ratio.
Got it. Thanks.
We'll probably, in other words, we think it will contribute to the scatter, intrinsic scatter of the relation, but we don't think it would change the slope of the normalization.
Well, thank you very much. We need to move on to the next talk, but if there's more questions, please go ahead, put them in the chat, put them in the AGNSC channel. And we'll move on to the next speaker, Paula Sanchez, searching for changing state AGNs in large data sets. So please take it away.
Can you hear me?
Yeah, we can hear you.
Okay, thanks. So today I will present you one of our most recent works. This work has been just accepted in the Astronomical journal. So I invite you to go to the archive today. You will see the paper posted there. So the motivation of this work is to search for changing state AGNs in massive data sets. And maybe you know what these kind of sources are, but just a reminder. So changing state AGNs or changing look AGNs in the optical range are defined sources that present drastic variations in their broad emission lines, sometimes even changing their classification as type 1 or type 2. And normally when we see these transitions, we also see a high variability in the optical range. So this is one of the first examples that were studied for a changing state AGN, where we see here a drastic variation in the G band and also the disappearance of the broad lines. So in order to understand the physical mechanism behind changing state AGNs, we need to follow up these sources on real time. And for the moment, there is, at least as I understood, only one work who has been able to do this. This work was presented by Claudia Ricci and collaborators, where they follow up a changing state event right after the event was starting. And they use X-ray observations and also optical spectroscopy. And they conclude that probably this event was related with a tidal disruption event. And this is the only event that has been studied in this way. But if you want to do this for a larger sample, we need techniques that allow us to search for these kind of sources on real time. And in the past, there has been some attempts to do this, but using archival data, not on real time. This first work by Chelsea McLeod in 2016 used SDSS photometry and Pan-STARRS photometry and selected candidates measuring the variability amplitude. So they selected sources with amplitudes higher than 1 magnitude per year. And in that way, they select a sample of changing state AGNs. And more recently, Matthew Graham and collaborators use a more sophisticated techniques with Bayesian blocks and sleeping wavelet variances to select candidates using Catalina data. However, we want to test an approach that is different because recently there was a paper by Supermassive and collaborators proposing that when we see changing state events in the variability feature space of damp random walk parameters, they tend to look as anomalous sources. So they can be classified as outliers. So from this, we consider that maybe we can use anomaly detection to search for these kind of sources. And this is the work that I will present today. And in particular, now we are using data from the Zwicky Transit Factory, or CTF, using data release 5. But the idea is in the future to apply this technique to the Vera Rubin data. So I'm a member of the LSST broker, so since we have access to the alert stream, we can predict the behavior of these sources using, for instance, data releases, and then check the variability in the alert stream so we can find these sources in real time. So since this is very new, anomaly detection is a very popular technique in machine learning. I will explain you the techniques that we are using before I tell you the results. So anomaly detection is a technique that is very popular in machine learning and is related with the identification of rare events or observations that differ significantly from the majority of the data. So there are several types of anomaly detection, but the ones that are more popular in astronomy are out of distribution anomaly detection, where we search for sources that look unusual compared to the regular datasets. For For instance, here we have two variability features or properties for the sources, and the normal data is clustered in very specific regions, and the anomalies are located outside these clusters. And we also have contextual anomaly detection, where instead of discovering sources that are unknowns or are particularly rare compared to the regular data, are sources that are normal but suddenly change their variations of their behaviors. So for instance, here we have a time series that is varying with a periodic signal, but suddenly we have a drastic change in the behavior of the source, and then we recover the periodic signal. So this kind of anomalies can be detected using contextual anomaly. So first I will tell you techniques to do out-of distribution anomaly and then contextual anomaly. So in this work in particular, we are using a technique that is called isolation forest, which is a very popular anomaly detection algorithm, which basically is based on decision trees, where we measure how much splits we need to do in order to isolate a given object. So anomalies are the ones that are more easy to isolate. So for instance, here we have anomalies that are isolated in the very splits of the decision tree, and then the regular objects requires more splits. So here we have a more concrete example where we have a red circle and green circles. The red circle is anomaly, and you can see here that using only one split, we can separate this object from the rest. So we can use the number of splits or the distance from the leaves to the first node of the tree as an anomaly score. So this is isolation forest. And to do contextual anomaly, we can use more sophisticated techniques. So in this case, we are using an autoencoder. So this was presented by Matthew yesterday, so I won't go to the details, but basically autoencoders are neural networks that learn a latent representation of a data set by compressing the information in a vector that contains a compressed representation of the data. And then with a decoder, we can decompress the information and produce a reconstruction. But in this case, we are using a modification of the more classical autoencoders, where instead of using one single vector to represent the latent space, we use a probability distribution. And in this case, we are using multivariate normal distributions. And these are called variational autoencoders. So the main difference is that instead of having one single vector, we have probability distributions that are characterized by a mean and a variance. And the main advantage of doing this is that we can use these models as generative models, because we can sample different vectors for the latent space and generate different representations every time. And also this allows the variational autoencoder to have a latent space that is smoother and that cluster together sources with similar properties, which is not the case all the time with autoencoders. So in this case, we can use this kind of latent space for anomaly detection. And in particular for this work, we are using a modified version of the more regular variational autoencoders that use recurrent neural networks in the encoding and in the decoding. And these are very popular for sequence-to-sequence learning, like for instance, for time series. And the advantage of doing this is that we can deal more easily with likers with different lengths. So then, since we have this variational autoencoder, we can do two types of anomaly detection. So one, for instance, is to do contextual anomaly, where we compute the reconstruction error of the prediction, and then we can use this as an anomaly score. So for instance, here we have this time series, where in this case, the reconstruction will fail. So it will have a high reconstruction error, and the source will be classified as anomalous. And also we can do out-of-distribution anomaly detection using the latent space as a vector of features, together with a method like isolation forest. And this has been done previously in astronomy. This is a very good example by Villar 2021, but this is for supernovae. So the idea is to apply all these techniques for AGNs. Okay, so now that we have all the techniques, how can we do anomaly detection for AGNs? Well, we were inspired by the work presented yesterday by Matthew. This was presented in this paper, Tachibana 2020, where they proposed an autoencoder architecture to model AGN likers. One of the advantages of this architecture is that it allows to not only make a reconstruction of the liker, but also to make forecasting. And in particular for this project, we are using a sample of AGNs from Milliquas and Roma with CTF likers in data release 5. And we restrict the sample to sources with that are point sources and with more than 2 years of data. And in order to train the model, since we're doing anomaly detection with this model, we use a balanced sample where we take all the sources with physical properties available from the literature and selected as a sample that is balanced by means of the luminosity and the black hole mass. And this is important because we want to avoid the method to classify as anomalous sources that are just less luminous or very luminous with respect to the total sample. And also, in order to avoid any correlations between the latent space attributes and the length of the liker, we balance the data set by the number of epochs per liker. And this is more discussed in the paper, but you can see this is crucial to do anomaly detection with these kind of techniques. And to train the model, we are using mostly regular quasars, but to test the algorithm, we are also including other classes like blazars and host-dominated AGNs. So the main changes that we do to the original architecture is instead of using a recurrent autoencoder, we are using a variational recurrent autoencoder. And also the units that we are using, instead of using LSTMs, we are using GRUs. This is a small change. But the rest of the architecture is exactly the same. So we are using the same number of layers and units. And we tested other modifications like more layers, different number of units. But at the end, the results were very similar. So we decided to keep the same number of layers and units as in the original paper. So we train the model with this balanced training set. And here you can see some examples of a set of random likers that we selected from data release 5. In black, you have the original likers. In red, you have the predictions. And here you have the reconstruction error for the training set. So this reconstruction error is measured using the original likers and the predictions and the photometric errors and the errors of the predictions. And here you can see how these latent space attributes, in particular, we are using the mean of the latent space, correlate with the number of detections. And here you can see that the correlation is very low, which was the case for the case of the original architecture. So we decided to keep this version that is less biased towards the number of detections per liker. So once we trained the model, we applied the algorithm to the full set of likers. And we selected as anomalous the sources that were that had very high reconstruction errors. In particular, we are using this threshold, a reconstruction error higher than 3. And here you can see some examples for regular quasars, host-dominated AGNs in red, and BLACs or blazars in pink. And most of the blazars are considered anomalous by this technique. And for the case where we have good reconstructions, we use isolation forests to classify the sources as anomalous. So in this case, we use a 2% contamination and selected as anomalous the sources that were below this threshold. Sorry? Okay, we continue. So using this technique, we detected around 9,000 anomalies. Here you can see the fraction of anomalous sources per class. So in general, blazars tend to be classified as anomalous by this technique. And this is very interesting because we know that we expect that the variability of blazar is consistently different respect to the regular quasars. So since we're training with regular quasars, is a good result to see that blazars tend to be considered anomalous. And the fraction of anomalous regular quasars is of the order of the thresholds that we were imposing. So this is also a nice result. And when we check the anomalies that we are detecting, we found that a high fraction of them is dominated by problems in the photometry, like these examples where we have this ghost in the CTF images that are not easy to remove using the flags provided in the data release. And we also found that some sources from the original catalogs were misclassified sources. For instance, here you can see two examples of variable stars. This is a cataclysmic variable and a young star object. So these sources were classified as anomalous by the algorithm. But if you see, for instance, the classification in the LSST classifier, there can be considered variable stars.
You have 3 minutes left.
Okay, thanks. So we use this set of candidates to search for changing state AGNs, and we selected these candidates as changing states when they show evidence of flaring activity or an abrupt increment or decrement in the luminosity. So we visually inspected all the candidates, and we identified 75 candidates. And here you can see some examples of the candidates. This is the sample of sources with recent SDSS spectra, which was more or less obtained at the beginning of the CTF survey. And we are currently in the process of confirming the candidate set. So we are collaborating on this with Matthew Graham, who is already taking some spectra for this sample. But for the moment, we know that there are 4 sources that were in the original sample of Graham 2020, and also an additional 2 that were already confirmed spectroscopically. And there are 28 candidates in common with using other techniques, and this is a work that Matthew Graham and collaborators are preparing. And something interesting that we found is that a high fraction of our candidates show some shapes in their light curves that are reminiscent of those shapes that we see normally in X-ray binaries in the X-ray energies. And we call this the plateau feature. So this feature is characterized by a sudden increase or decrease in the light curve together by followed by a very constant light curve. So here, for instance, you have this drastic decrease, and then you have constant, or the opposite, you have constant and then a drastic decrease. So these kind of shapes are normally expected to be detected in AGN light curves, but with time scales of several thousands of years. So it's interesting that we're observing this with time scales of hundreds of days. And we are still in the process of understanding whether this is something that is actually physically interesting, or this is just an artifact. So in summary, we are doing real-time detection of changing state AGNs in order to be able in the future to follow up these sources on real time. To do this, for the moment, we are using anomaly detection, and we are using this operational recurrent autoencoder architecture to study the full sample of AGNs with CTF light curves in data release 5. And from this, we detected around 9,000 anomalies, and but most of them were bogus candidates, so problems in the photometry or misclassified sources in the original catalogs. But we were able to identify 75 promising candidates, which are still in the process of being confirmed. And some of the candidates present these particular shapes that can be associated to the behaviors that we see normally in X-ray binaries, but further work is needed to confirm what is producing these kind of variations. And finally, some message that I want to give you is that we cannot use anomaly detection blindly to do any kind of a study, because when you do anomaly detection, normally you also see other kind of things that are not with an astrophysical origin. For instance, you find problems in the data or sources with misclassifications. So if you want to see more details, you can go to the archive today and you will see the paper there. Thanks.
Thank you very much. So I see Yu-Ching Chen has his. Go ahead, Yu.
Thanks, Paula. I'm genuinely curious. So looking at some of the candidate changing state agent you identify with anomaly detection, they look like extremely variable objects. So if I just naively select extremely variable quasars or AGN based on the light curve, would they be all selected by this anomaly detection technique, or are there some things selected by just looking at the magnitude change, but not identified by this anomaly detection?
Yeah, in this case, we're not biased towards the most variable sources because we are normalizing the light curve. So what the algorithm is seeing is not the original light curve, but it's a normalized version. And actually, there are some very variable sources that are not classified as anomalous by the algorithm.
Okay, I understand. So there's a difference between the magnitude cut threshold in defining state transition. But what is a normal agent light curve?
That's what the algorithm is telling you. So this is something that, is, deep learning is kind of a black box, so it's hard to interpret what the algorithm is considering anomalous, but basically is anything that the method is not able to reconstruct because it's anomalous respect to the regular data, or when you see the latent space, sources that had properties that are consistently different respect to the regular population. So for the case of the latent space, it's like using, for instance, features and selecting sources that have very particular features respect to the rest of the population. So at the end, you have your normal distribution that is dominated by regular quasars. So it's everything that has Likert shapes that are consistently different from regular quasars.
Okay, thanks.
And I see we have a number of questions in the chat. So can I start with the first one? So Ilsan Yun asks if you consider the case where the source does not belong to any of the classes as an anomaly?
Yeah, for the moment, we are using a sample of sources with labels. But for the second part of this work, we will classify the full data release and use this as a baseline for anomaly detection, because we needed to test the model somehow. So we started with this sample of sources with labels, but yeah, it's the plan for the future to apply this for the full set of Likers available in CTF and in Rubin in the future.
Michael Strauss asks about the comparison to X-ray binaries and says that the amplitude of variability in the X-ray binaries is much larger than for the changing state AGN that you showed. To what extent can you draw the analogy between the two objects?
Yeah, this is something we are just studying now. So I sadly cannot answer that question properly. For the moment, we are just focusing on the shape of the Likers, but we know that we need to study this in more detail. So the idea is to get spectra for the sources at different moments of the light curve so we can understand what is going on. But yeah, it's hard to tell anything with the information that we already have. Sorry.
Thanks. And so I see there's a few more questions, but we're actually at the time. So perhaps we can save those questions for the discussion session. And cut them there. But before people
on variability from intermediate mass black hole candidates. This in the context of supermassive black hole studies with the legacy survey for space and time. This work is being carried out together with Franz Bauer and Paula Sanchez Saez. So, so as a broad motivation, we would like to know and understand what is going to be possible to do, what could be done with the advent of LSST data, But as well, we want to understand the caveats that we might encounter in this interesting journey by exploring this mass regime that is still poorly investigated. Additionally, we would like to probe the black hole physical properties in order to, for instance, understand if the accretion mechanism is a constant for all black hole masses that we can see. And finally, we would like to confirm the AGN nature of intermediate mass black holes candidates via variability. Another thing to point out is that by investigating intermediate mass black holes, we can have insights on the origin and evolution of supermassive black holes. Additionally, we are using now CTF data, in particular force photometry on the different images. And with the advent of LSST, with all this humongous amount of data that is going to bring, we expect that the sample size will increase in at least 1 or 2 orders of magnitude with better photometry and hopefully better calibration. I want to stress here that we think that we are using the right approach by using force photometry on different images, because in this way we can deal in the best way possible with the host contamination, the host contribution to the emission. And this is the closest we can get to what beta Rubin is going to provide. So let's go straight to the sample. We are using a sample of around 700 candidates that come from mainly 3 works: Greeny and Ho 2007, Dong 2012, and Chilingari et al. 2018. These works used SDSS data that released 4 and 7. So our sample will inherit some of the caveats that this survey might have. The distribution on the sky of these sources is, as can be seen in this figure. And something to point out is that these different works used a broad line approach to calculate the black hole mass using the H-alpha line, and they trace different parameter space in black hole mass, as can be seen in this figure of Eddington rate versus black hole mass, where you can see the distribution of the different subsets coming from these different works. So one important characteristic of our sample is that it's mainly composed of extended sources. This can be seen in this histogram of the PS score, which is a morphological star galaxy score provided by Pan-STARRS from the work of Tachibana and Miller 2018, where sources with PS score close to 0 imply that they have a higher likelihood of being extended. So this can be seen in the lower panel, where I present 2 examples of sources with PS score equal to 0, images of the Pan-STARRS stack data of Y, I, and G filters, and you can clearly see that these sources are extended. As I mentioned, this is crucial because this means that we are going to have a great contribution from the host to the observed flux. Now, once that we have this flux, we have light curves as shown, for example, in this left panel, and we have to clean them. So we are now following the prescription from Maskey 2018, but we are exploring different metrics in order to clean these light curves in the best way possible. Here you can see in this example at the right, cleaning of this particular light curve using metrics related to air mass, the 0 point, and the RMS between the difference between PS1 calibration and instrumental magnitudes. This is a work that is still going because we are exploring in this metric space for parameters that helps us to clean outliers like this one cleaned right here, but without removing any real data. So now I want to share with you some of the variability features that we are calculating and using. For a broader discussion, I invite you to read the paper from Sanchez 2021 and the reference therein about the light curve classifier from Alerce. But basically what we are doing is to compute these variability features using at least computing these variability features in light curves with at least 6 detections in a given band. So for instance, we are computing Mexican hat power spectrum from Arevalo 2012, which is related to the variance of the light curve for 2 different frequency regimes, and a variety of other indicators related, for instance, to the damn random walk modeling, the structure functions, the excess variance, the probability of the source being intrinsically variable. And all these particular features are computed with FATS Python package from noon 2015. Something to point out as well here is that most of these variability features are going to be present in LSST data products, and this is crucial for us to characterize this kind of sources. So let's go to the analysis and results. To make the presentation easy, I will present only results in the CTF-G band, but the I band and R band present similar results. So although CTF force photometry indifference images are the right approach to deal with these host contaminated sources, we still have some contribution from the host that has to be dealt with. So to do this, we consider a subtraction of a fraction of the minimum value of the flux to the total light curve. And we explored a variety of contributions of this fraction of the minimum to be removed from the light curve. So here I present in this right panel figure a comparison of 2 extreme cases where I present the relaxation time from damn random walk modeling. In the y-axis, we have the case where the AGN has only a variable component. So we are subtracting the entire value, 100% of the minimum, to the values of the light curve. And in the x-axis, we are in the presence of this other extreme case where the AGN has a significant constant component. So as the AGN has this significant constant component, we are not removing any percentage of the minimum to the light curve. But as you can see, the bulk of the points are concentrated in the one-to-one relation. So by studying this, and what is shown here is that this consideration of subtracting a percentage of the minimum to the light curve does not affect significantly our results. In this particular figure, we can see that these points are color-coded by Eddington rate. And here we can see that the one-to-one relation is populated with points with sources that have Eddington rates between 0 and 1, and that the points that are more scattered present higher Eddington rate. This could have 2 explanations. One is that we expect that the sources with higher Eddington rates will have lower variabilities, will lower amplitude of variabilities. Or it could be that since these high Eddington rate sources are related to lower mass black holes, it might be that these estimations of these particular sources are not as reliable as we might think. So in any case, as we saw that we do not have this strong variability in our results, given the different subtraction of a fraction of the flux to the light curve, we decided to stay in the case where the AGN and the host, the AGN constant part and the host contributes equal amounts to the emission. Now, then we calculated some variability features to this sample. For instance, we calculated the probability that the source is intrinsically variable. We found that at around 92% of our sample presents variability according to this parameter, having values greater than 0.95. But we cannot trust this parameter alone because it does not take into account some systematics as the host contamination. So we had to take into account other metrics, other parameters, such as the excess variance, which relates the standard deviation of the light curve, the photometric error, and the average magnitude. And you can see here that according to this feature, most of our sample, around 65%, sorry, is dominated by noise. So we selected a combination of features in order to select or to define the most variable subset within our sample. So that is what I present here. So the most variable subset conditions are the following: excess variance greater than 0, p-var greater than 0.95, and dumb random walk modeling relaxation time greater than 1, because this is the point that from which we cannot trace other lower timescales because of the cadence of CTF. And based on these conditions, we found that around 17% of our sample have robust variability. For the non-variable subset, the conditions are the opposite, and we found that they represent around 5%. Here in this figure on the right, on the left, I present again tau2 versus tau1, color-coded by excess variance. But here, what I want you to see is that these darker points represent the most variable subset, and the yellow points represent the non-variable subset. And at the right, you can see the light curves for some of these particular sources, 2 non-variable and 2 variable. You can see the non-variable in the extremes. And you can see that these points that we might think that trace variability have large error bars. So they are probably noise. And in this case, we almost do not have any variability. And in the panels, the middle panels, we can see that these light curves indeed trace stronger variability. Okay, so now I show you here the Eddington ratio versus black hole mass at the left. We can see that we have a distribution of black hole masses, which is not smooth. It is kind of discrete, and that we have a lot of sources. A great number of our sources are super Eddington, which is a little odd, but interesting at the same time. Another thing to notice here is that the subsample composed of variable sources and non-variable sources span all the range in mass and Eddington ratio in our sample. On the right, we can see the redshift distributions in the sample. And what we can notice here is that the non-variable subset trace a population that is a little bit further away compared to the variable subset. Nevertheless, our sample is really local. Okay, here, basically really quick, what I want to show you here is what I'm showing here is the relation of some black hole properties as redshift, black hole mass, and Eddington ratio with respect to the variance of the light curve given by the Mexican high power spectrum in 2 frequency regimes, the low frequency regime of 100 days and the high frequency regimes of 10 days. What this is showing us, what this is telling us is that since these plots present large dispersions, we still have to clean our light curves better, in a better way. And we expect that with the data, with better photometry from LSST and hopefully a better calibration in the difference image in the first photometry of the difference image, we can trace potential correlations here. And what we hope is to fill the gap that Colin was showing in his presentation in the tau versus black hole mass, for instance. Okay, so as a summary and future work, we have found within our sample that we have around 70% of sources that present reliable and robust variability that can be trusted. We expect that this number can grow with the advent of LSST because it will clearly improve the noise characteristics of the measurements. And we hope that this value can also scale with size as LSST will bring enormous amounts of data to the table. Additionally, with these kind of results and with this study in particular, we would like to understand what is the infrastructure that it's going to be needed for LSST by using CTF, in particular force photometry on the difference image, which deals again with part of this host contamination. But that there are some uncertainties that cannot be solved just with LSST. Some caveats, just as the limiting magnitude of the source, the intrinsic limiting magnitude of the source, or the contribution of the contamination of the host to the emission. This maybe could be approached by SED modeling, but we will need much better spectra. We also think that the blending will play an important role, but because at the end, what we want is to isolate the emission from the nucleus. So that's it. Thank you very much. I will be happy answer any question or receive any comment or suggestion to this work.
Thank you very much, Ernesto. Matthew, go ahead.
Yeah, Ernesto, nice work. My only question is, with the forced photometry, are you including color terms of the AGN? Because with the ZTF forced photometry, those are still not color calibrated. So I'm wondering, I know that the lack of color terms has caused an issue of increased scatter in just the regular photometry, but I suspect that there may be an effect there still with the difference photometry.
Can you repeat the question? I didn't get it.
Yeah, so the regular photometry that ZTF puts out is calibrated on a 0 point, but it has no color terms added to it. You need to do that manually. This is true, and this has caused increased scatter in just regular light curves of AGN that I know the LSA folks have seen in the past. This is also true for the forced photometry that our forced photometry service puts out. Those light curves are still uncalibrated according to color. And so there may be an intrinsic scatter in there that's coming from the color terms.
Yeah, absolutely. So we are following the prescription from MASCI from the manual of generating light curves with forced photometry from CTF, but we are using our own. Yes, we are using our own 0 point in order to calibrate the light curves because for our particular case, the prescription is not as useful.
No, the 0 pointing is fine,
expecting.
but the MASCI manual does not mention that. I think this has only been realized recently, or that that the difference photometry still is still not color calibrated. And so there may be an additional color term that you need to put in there, but it's a little unclear what that might be.
Just to answer, we haven't put it in, and that's one of the future works is actually to recalibrate on a CCD level the 0 point.
Yeah. Now we're hoping that there's going to be revised calibration data coming from ZTF sometime this year, which may make this easier for you.
Matthew, but can we avoid those issues if we use single CCDs? And we don't combine CCDs?
No, not even CCDs, because each CCD it's actually a quadrant. It's the base level for ZTF data reduction rather than CCD. So it doesn't. This is a discussion we can continue offline. It's just I think there's a certain caveat that you might need to just double check. But I would not be surprised if there is a term of scatter in your data that may be coming from the lack of color terms in there, because we do not calibrate to color terms currently anyhow, even in our forced photometry.
I will take that into account.
Yep. I think Colin also has a question.
Yeah, thanks very much for the nice talk. Sorry if I missed this, but I'm wondering, how did you get the bolometric luminosity to compute the Eddington ratio? That's my
so for some of our sources, the Eddington ratio is given, and for the other ones, we are using the luminosity from the H alpha, and we are using a calibration related to the volumetric luminosity in order to calculate the Eddington ratio.
Cool. Yeah, I'm just curious if the host galaxy contamination would be a concern for that, but I'm not
Say
sure.
again, sorry.
Just wondering if the host galaxy would possibly contaminate the bolometric luminosity.
Yes, I think possibly, that's a possibility, because this calibration to transform from luminosity of the H alpha line to the optical luminosity and then to the bolometric luminosity is a rough estimate. So yeah, it might have present some scatter there.
Interesting. And then my final question, did you look at the minimum cadence of the ZTF light curves? For example, for NGC 4395, one of the issues I ran into is or even for any light curve that varies very rapidly, if the time scale is sort of within a factor of a few of the cadence, similar to the cadence, sometimes the time scale just sort of, it will just spit out the cadence. For example, if tau is much smaller than the cadence, then it will just give you the cadence. So I'm curious if you put any constraint on the minimum cadence of the light curves.
Not all the light curves, but for the most variable subset, we did. And yes, absolutely, for some of them, ones that we are calculating these timescales, we are calculating the cadence or sometimes the length of the light curve. So that is something to take into account when studying larger amounts of data, of sources. And we still have to work on it in the future when we are cleaning better, for instance, the light curve or selecting particular timescales. But yes.
Yeah, thanks. I think for most of your sources, a cadence of 2 or 3 days should be good enough. Right. Thanks.
And Mauricio, you also have a question?
Yes, thank you. Thanks for the talk, Ernesto. I had a sort of a question and a comment. When you selected the most variable sources, then usually when you select invariability to do variability study, you will end up having some selection bias inevitably. So I was wondering if you look into that as well. And then I was wondering if the most variable source that you get are still some extended source with the host galaxy, or you're picking up more the quasar-like objects?
In general, we think that regarding your second question, we think that the most variable sources are extended as well. We have very few point-like sources, just a couple of them in the 700 set. So yes, they are pretty much extended. And regarding the selection effect, we haven't looked deep into it, but absolutely, we have a selection effect there, given the constraints and the limits that we are using in the features to select the variable subsample. So yes, we have to look into it. Thank you.
Thank you very much, Ernesto. We're going to stop sharing the screen. So now we have sort of free open discussion time. So perhaps the first thing, there were a number of questions and a number of discussions ongoing through the other talks or about the other talks. So I wanted to give opportunity if anybody wants to raise a question about if there's something that didn't get discussed, those talks that you think it's interesting, anything you weren't able to ask any of the previous talks. Sorry. I don't see any raising hands. So I guess one of the one of the questions I had, and I think it might be good to start framing a discussion, is so we saw, well, of course, today was very focused on variability and a lot of what we can learn about variability. But one of the things is that once we start to wanting to learn about the physics of these objects, it seems very clear that we need to consider. I'll get to what Michael is asking. Okay, in a second. But it seems like we do really need to consider things like redshift and type of AGN. In order to actually make any progress to transform all of these detections of variability and characterizations of variability into physical processes. So I don't know if you or any of the people working on variability have been considering what kind of, how would a follow-up on LSST would actually look like, or given that photoseeds will likely have significant uncertainties, how far can you go using photoseeds into constraining the physical properties of these objects?
I wonder if I can phrase this in a complementary way, which is, what kind of biases exist in our existing spectroscopically confirmed quasar catalogs, and to what extent do we need more characterization, either redshifts or more completeness in the quasar catalogs, in order to not bias ourselves in looking for trends with luminosity? It's a different twist on the question that you've asked. And I don't have a good answer.
So regarding variability, something that we have found while developing the LSST broker is that we have in the quasar catalogs, most of the sources are blue quasars, and when you apply variability techniques to search for AGNs, there is a high fraction of red sources that appear. And if you see the fraction of red sources versus blue sources in the spectroscopic catalogs versus the variability catalogs, it seems that with variability, you can populate the red part of the color code diagrams.
And are those red sources typically sort of mildly obscure AGN?
They are mostly host-dominated AGNs, where you have the color is dominated by the host galaxy. But you still see the variability because they are faint sources that are more variable. And in the alerts are particularly easy to detect them since we have subtracted the host component. So it's easy to get the variable signal. So if you see the fractions, there is a consistent difference.
So actually, that actually relates to a question I had about your talk that I didn't get to ask Paula. So you showed that there was a significant fraction of type 2 sources that were detected as this sort of anomalous, through anomalous detection. Were those primarily changing state AGN, or were this sort of host-dominated things, or what kind of type 2 were they?
Sadly, it seems that the type 2s were misclassified sources. So if you see the spectra, it seems that they are 1.9, 1.8 sources. So that's why you're detecting variability. And since these sources are also kind of dominated sometimes by the host, the variable signal is damped by the host. So you see an anomalous shape respect to the regular quasars. So yeah, but this is because we are restricting our sample to point sources, and type 2s are more local, so they can look extended. The known type 2s, I mean. So if we use a larger sample with not only point sources but also extended sources, maybe we will be able to search for just to detect sources like type 2s changing to type 1. So it's the restriction of using CTF data releases, which are not suitable for extended sources.
Okay.
But the point source versus extended source, just a comment, is going to be a thorny issue that we're going to need to have some sort of prescription for as we move forward. So it's probably a point of discussion in whatever task force we designate.
Yes, I think that's crucial because currently, if we want to do this massive analysis with TTF, it's impossible to do it for extended sources unless we do some corrections. So we are trying to do that, but it's not easy.
Unless there was forced photometry for everything.
Yeah, so the tool that is currently available, you can just download 100 Lakers per day, so it's not easy to do massive analysis, but yes, I hope you soon will release a version of the pipeline that allows you to get more light groups.
Gordon, I see you have your hands raised.
So I guess related to your original question and Michael's rephrasing, what are our best sources of mid-infrared and X-ray flux-limited spectroscopy? Mid-infrared and X-ray selected objects where we've got spectra down to a flux limit, not necessarily of things that are AGNs.
Well, from an X-ray perspective, it depends kind of what solid angle you're after. If you want to go really deep, you can do the Chandra deep fields, which have a very tiny solid angle, that are pretty good. And I think the spectroscopic completeness for Cosmos is pretty good, for example. And hopefully in the near future, with facilities like PFS and Moons, there'll be a lot of headway on the other deep drilling, at least significant parts of the other deep drilling fields. Is that what you're after, Gordon?
And isn't there E-Rosita follow-up in Sloan 5 in the opposite limit of large fraction in the sky?
That is starting, yeah, with Sloan 5.
And for
it's early days, but yes, certainly that'll maybe a lot of headway there in the coming years.
Yeah, I mean that's what I'm talking about, right? It just is important. Like if we want to know what we're missing, we can't be just relying on spectroscopy of things that somebody had thought belonged to their science category, right? You really need sort of flux limited spectroscopy at some level.
Mm-hmm. Well, I'm very keen for people to continue spectroscopically targeting all the X-ray sources we've recently released in the deep drilling fields. By all means, please go hit those as hard as you can with whatever facilities you have available.
And I think in a wider area too, the foremost surveys, in particular the one that France is leading, would actually help a lot in there as well. And there's, I think, a lot of E-Rosita follow-up is going to be done with foremost.
If you want infrared selection, the DESI Quasar selection is partially based on infrared. The WISE W1 and W2 bands in particular.
Yeah, to a shallower level, EBOS as well had some, but I guess there's not that much.
Basically, WISE was a veto for EBOS. We required basically an XD prediction that something was a quasar, but then if you require WISE detection too, it ends up cleaning up the sample a lot. It wasn't so strongly based on WISE.
I think that Sloan 5 selection is not necessarily what we want here, right? I mean, we want to be probing things that are more lower luminosity AGNs, right? I mean, that's what we're missing.
Yeah, and the DESI selections do get you a fair number of lower luminosity AGN around 0.8. 0.8 to 1, we seem to have some degree of pileup, I think even from the LG selection. That may or may not be, it's not complete. It may or not be what you're most interested in.
I mean, I think, Gordon, then you're really asking to do just a magnitude limited survey and then see what you get, right? So the galaxy samples from DESI or from Foremost are probably going to be most relevant in that sense, right? Because they're blind to selection.
Well, they do have a morphology cut, so that there may be concerns.
Most of the samples don't. Only the Quasar sample has a morphology cut.
So the galaxies do not require to be fuzzy?
No.
I see.
We consciously made that choice.
Okay. With this in mind, or what else did you have in mind?
Well, you just don't necessarily believe the morphology classifications for the imaging.
Fair enough.
And it was, a couple % effects on the selection.
Mm-hmm.
Especially for the ELGs, they're barely resolved if they're resolved at all. So you don't really want to be requiring they don't look like a PSF when you can't tell the difference.
Got it. Okay, that makes sense. You must have had some, you do have color cuts, so those are regions where ordinary stars are not supposed to live very much, so it should be
it depends on the sample.
Yeah.
They overlap with stars in some cases, but we're at fainter magnitudes for things like ELGs where we do overlap with stars, and at those faint magnitudes, galaxies dominate.
Mm-hmm.
And I guess a question is, I don't know if people have been thinking about how to incorporate redshift uncertainties, for example, into the analysis of structure functions or similar variability measurements.
Do you repeat that, Roberto? I didn't catch that.
Oh, so no, I was wondering if so people have been basically thinking about ways of marginalizing, so USS using the full PDF from the photometric redshifts to actually try to marginalize over the uncertainties and get some physical constraints. So I don't know how easy it is to make some of the or a lot of the analysis that are being done with marginalization over uncertainty in redshift. So I do realize this is not a super well constructed question, but it's primarily I'm not doing a lot with variability analysis. Just more a question for the experts here.
Well, I presume you measure the structure function in the observer's frame, which doesn't care what the redshift is, and then your interpretation of that would have to marginalize.
But I think Roberto's point is crucial if we want to use Rubin for massive analysis, because we won't have redshifts for every Liker. And with Foremost, we will have some, but if we want to do the kind of analysis that the Metra is doing, for instance, we need to identify these kind of caveats. Like, so because if you find some correlations, for instance, between the variability amplitude and the black hole mass, you need to correct also by redshift all the time. So I think it's something maybe we're not working on right now, but it's something crucial for Rubin.
And particularly, it will be likely very specific or subsamples on which we will have very little to know spectroscopic follow-up, right? Particularly as we start probing towards the fainter end of what we can do.
Yeah, actually, if we want to use the Likers to measure black hole properties, we need to do this kind of analysis, for sure.
I'm also worried that we have to have reference sample of non-variable sources to some extent, so that we will be folding in the uncertainties in the redshift, both of AGNs, but also of normal galaxy, because getting a handle of possible systematics due to the rest of the population, you require comparable sample in terms of redshift, of magnitude, and so on. There is also another issue that I was thinking before from the previous presentation, and it was to think at some point if we can put together both X-ray, for instance, and optical variability to some extent. So we would probably not have anything simultaneous except maybe on specific areas, or but we also should think about if it's possible to do any joint analysis of some data sets and try to constrain further if there is a link between these two, or if they're both related to underlying physical parameters, we can trace going both through the X-ray and the optical side.
I mean, I don't think you have to worry about simultaneous, because even if your X-ray and optical data are simultaneous, they're not, right? So, I mean, the scales are just too different, right? So,
yeah, you're right about that. Unless you want to really look at some reprocessing, but that will be very specific case, or it has to be done statistically on an ensemble analysis.
So I don't know if anybody wants to add more to this point, but otherwise we can actually move to what Michael was mentioning, that yesterday there were a lot of technical questions about processing of the alerts, and I think today we might have the experts to answer. I think Yasra is on today's, might know more about those very specific technical questions, but I don't know if anybody would like to bring back some of those questions or had specific things to. I don't know, Michael, if you had any specific points that you wanted to discuss.
Just want to say hi. Yes, I'm here and happy to answer any questions about pipelines if you have them.
yes, sir. I mean, I could phrase this better, and I think I have in some community posts, years ago. But I mean, basically, one of the questions is we were talking about is, what light curves are we actually going to have, right? That is, if your light curve is actually from the difference imaging, and you don't have flux information, from the same model, right? Like, what we don't really have what we would think of as a true light curve, right? That is, you don't have the brightness and the variability amplitude measured in the same way.
Okay, I saw, and so I signed on right before the meeting ended yesterday, and I saw a comment in the chat that was also kind of worrying that I wanted to address as well, which was that somebody said something about us not having light curves for wide field deep in IRD 1, which is not the case. And so I'm worried that maybe folks are confused about AP versus alert production versus data release production light curves. And could I have like a couple minutes to clarify with everybody the difference between those?
Yeah, absolutely, please.
Okay, you know what? I'm gonna share my screen with that has the pipeline, just the pipeline. Okay, so the first thing is that calibrated light curves are a data release production data product. So in this image, the output catalogs are these red parallelograms, and the light curves are going to be in the forced source table. So for every
can you please display it on a larger screen, like a view?
Let's see if I can just zoom in.
Okay, thank you.
How about that? Okay, so what the forced sources are, we're going to do co-addition and detect sources on the coads. And we're also going to do detection on image differencing done as part of data release production. So data release production is going to do difference imaging on all the visits that have been accumulated to date.
Using a single template throughout, correct?
Using a single template in data release production, using a single template throughout. There is that is the current baseline. However, that would be something that could be changed, is using different templates through
like the idea of a uniform template, I think.
Sorry.
I think the default that you described is exactly what the AGN folks want. That is, they don't want the 0 point changing every year or something like that, just to confuse everybody.
Okay, but because that's the current.
Just to be clear, was your comment that like it could be changed from out from underneath us, or could be changed if somebody wanted that? In which case, I agree with Michael, right?
Okay, so the current plan is, if on year 8, for example, using 8 years worth of data for a given region of the sky, we select the best seeing images from all 8 years and co-add those into a best seeing template. Now, what I was saying is that is the baseline. However, if somebody came along and made a really good argument for why you need up to year 3 coads for difference imaging in year 4 and up to year 4 coads for difference imaging in year 5, that we would accept those arguments. But the baseline now is best seeing coads for the full survey to date. And then for every union of all the DIA sources, that is the union of all the detections on the image differences and all the detections on the deep coads, which are going to go deeper than the single epoch images. For the union of all those detections, we're going to perform force source on the direct images, like we call these sometimes CALEXs or processed visit images, PVIs. Those are these guys, single visit images. So we're going to do force photometry on all the single visit images and force photometry on all the difference images. And those are going to be in one table side by side. You will have both.
And that will be PSF photometry or let's say, yeah, Franz is asking the same question.
Only PSF photometry. There's going to be no warping of galaxy shapes onto the single epoch WCS to do force photometry. No galaxy force photometry for.
So to the AGN folks, is PSF photometry the right thing? This is one of the things we were, at least I was getting confused about this.
No, for extended sources, definitely. And that's the problem we are already seeing in CTF.
Yeah, so, but what's the right thing to do? I'm a little unclear on whether there's an obviously better thing to do.
But for the difference imaging, the variable piece should just look like a PSF, right?
Yes, for the difference images, yes. That will be okay.
So this is exactly the reason why we're doing force photometry on the difference images as well, because the static part of the host galaxy, the static part, should subtract off, leaving just the difference.
Yeah, but sometimes you want a 0 point of that in order to look at luminosities, to the actual luminosity of the AGN. And the thing is, when you do subtraction, any constant component of the AGN also goes.
That's right.
Yeah, and so in general, will there be extended plus PSF fits for objects, or I guess you could always do an afterburner for that.
The fits are going to be done on the coads. So the 0 point so the force photometry on the difference image is going to give you the delta from the galaxy, so COAD photometry, which is
Right.
going to be
So to the degree that there's a non-variable portion of the AGN light or a floor on the AGN light, you'd have to recover that, as was being said, from the static imaging, and then
From the
add
template.
that, basically.
That's right.
From the template, I guess we have to have the reduction of the templates.
But exactly. So for the template, in general, where there'll be PSF plus extended fits, PSF plus search or whatever, or would that have to be an afterburn?
There will be. I'm not the best person to answer questions about galaxy modeling, but there will be a best decomposition, and then there was also the we call it the hop colors for galaxies. If anybody attended the algorithms workshop, this is we do PSF matching on the galaxies to get, and then do aperture photometry on those to get a consistent color of the galaxies. But yes, the fits on the COADs themselves are going to have component decomposition, but it would be best to get in touch with the Galaxy Science Collaboration.
Yeah, I think the question is, that'll be true for the COADs. Will we get the same thing for the templates? I think that's the question that we're
exactly.
Will we get everything for the templates that we'll get for the COADs? If the answer is yes, I think that gets.
Can we get the templates?
What they want.
Could the templates be made available? The images.
Yes. So okay. So within co-added images, these include all flavors of COADs that are produced. These flavors include the deep COADs for deep detection, which is where the objects get formed, and then also it also includes the best seeing COADs that are used for templates, and then it will also probably use it'll probably also include some kind of COAD used for measurement purposes. So like detection, measurement, and image differencing, these are all reasons to make COADs, but they all kind of have required different COADs to perform optimally. And all of those will be available. Whether there will be a catalog with the suite of measurements on the templates versus the COADs for measurement, I believe so, and that would come out of the DIA analysis section. So number 3. But I will make sure that is available in the tables.
So
I think this is a requirement for us.
Is that everything we need?
Okay, so let me see if I can summarize this, right? Which I think leads me to that it's not everything we need, right? So we're going to have difference imaging, right? That's forced with consistent templates going back in time for each of the databases. I think everybody is great with that, right? Certainly you can do your variability analysis with that, and then we're going to have deblended model photometry, yes, on everything but the difference images.
That's right.
But then the issue is we can't just take the difference imaging light curves and add that back to the model photometry.
Because extended versus point source is what you're thinking about now, or?
Well, for no other reason than the non-variable part got taken out.
No, but the non-variable part is exactly what you get from the processing of the template image.
From the PSF component to the fit to it.
Yeah, okay.
Yeah, you get that too. What?
Yeah, you need to do the blend. You need to do the blend in that image.
Right. As long as you
blend it into point source plus galaxy.
And then you add that floor. You add that floor to your difference imaging.
Yeah, I don't think, a lens astronomy like what John Silverman was talking about. I don't think that kind of analysis of point source plus sourcec is a routine part of the Rubin processing of co-edited images. That may well require separate processing.
So one question that just that wasn't super clear, or I'm still a little confused. So the detection is done on the coad, then you go into the image difference and image differencing, and you measure the positions of all the or the measured force photometry, where every source at the position of every source detected on the coad, or only at those classified as variables?
They do not have to be classified as variable. Every single peak that is detected in the deep coads will be force photometered on both the image differences and the single visit images, point source PSF photometry.
Okay, and the light curves will be available in the data release for every object then, not just for the variables. Okay.
Yes,
great.
and so when we can talk about alert production as well, which is different, which is not producing light curves, but will come with a pre-covery service that will perform force photometry on the visits that were in the last 30 days of a new detection that's above the 5 sigma threshold. And then it'll also make, there will be the ability for some limited number of sources to go back even farther. User requested pre-covery service.
So I have a related question. So I was wondering as well about the which source were being to be processed. And I understood for the test we did that there were the peaks that you observed. This is fine for probably a large part of the AGN, because sooner or later you will have a peak, although it depends if you're comparing only with the template and when the template is, because if it's too close in time, maybe the AGN didn't vary enough. So this will limit our ability to push the detection through variability. And so I was wondering if it would be possible, for instance, to propose to do this on targeted sample of sources, a subset in which we want to actually get the difference analysis on everything, even objects that are not detected as peak in difference images, everything that it's in a specific area of the sky.
So there will be force photometry performed on every detection in the coads. Now, let me make sure I understand your question right. So you're saying that, say you have a galaxy where the center of the galaxy, you're interested in doing PSF force photometry, not at the center of the galaxy, but like somewhere off center?
No. At the center, but let's say that it has a weakly varying source. So you don't really see it popping out in the difference image. So it's below threshold. So these type of objects, you may never do the force photometry on the difference imaging because they're never above threshold. And so there should be a subset in which I can ask, I want you to do the difference imaging at and the force photometry at the center of the galaxy for every galaxy that is in this part of the sky, irrespectively if it has varied or not.
That's okay. Well, that is in the baseline plan. Every detection, every galaxy that is detected in the coad, in the deep coads, will be performed on force photometry will be performed on both the difference images and the process visit images.
Really?
This is actually
every galaxy? I'm sorry, because I wasn't sure about it. I thought only the one that you see in the difference imaging.
No. Every galaxy that is detected in the deep coads, there will be force PSF photometry performed on the difference images and the PVIs.
Okay.
So one question for Mauricio. So when you talk about threshold, which threshold are you talking about?
Because for how I understood that the pipeline is working, Vincenzo has done some testing. He was getting the analysis on the image differencing only for object in which, compared to the template, you see in the image difference, you see a source. If you have a non-variable galaxy, you may have some residual noise structures, but maybe it's not enough to trigger a detection. So this makes very hard to assess, for instance, the noise systematics and so on. So I was wondering if it was possible to, if we were having image differencing also for objects that are not detected in the difference image with respect to the template. I know it's doing photometry around sources that are not in the image actually, but this can give you an idea of what the noise is and that we have to subtract the variability.
If I understand properly, that threshold is only applied for the alert stream. That's correct, yeah, right? The 5 sigma threshold or to generate an alert, but for the data releases, everything will be included.
Okay, so may I misunderstood that? Good.
Yes, one question about, will difference images be allowed to have negative fluxes? Because that was another group. If you have an Euler variable, it varies by 1 magnitude. So if you stack a bunch of images, you're going to get the mean magnitude, but then half your images are going to be plus, and the differences are going to be plus 0.5 magnitudes and minus 0.5 magnitudes. Is that going to be allowed, or does everything have to be positive and you'll just throw out the negative images and call it noise?
Detection on the difference images is run in both polarity, double polarity. So both positive and negative. Well, more than 5 sigma PSF detection will trigger an alert.
Okay, but if you're doing just the data release photometry, will you be reported like minus 0.5 magnitudes as the best fit value, or do you have some requirement that the measurement has to be physical, so therefore it can never be negative?
There's no requirement that the measurement be physical. The
magnitudes themselves will never be.
Oh, sorry.
Yeah.
The magnitudes themselves aren't going to be negative. You're forced to use fluxes. Yeah.
Well, we're not using. There's going to be no magnitudes in the database where baseline is nanojanskis. But I was going to say, so I was going to say, like, at no point do we assume that fluxes are positive, except the caveat to that is that Scarlet, which is the blender that we've been testing, it does make some assumptions about the shapes, the acceptable shapes of galaxies, mainly that they are monotonic and that they are positive. However, that the Scarlet models are not necessarily the object characterization which you get from aggregating the force photometry. So yeah, it's very possible that you will have force sources that have a mean negative.
Okay, thanks.
So, I mean, one comment is, I don't know that Wei Zhang has captured this perfectly, and in fact, I'm sure that he hasn't, right? But the intent of the data challenge, tables is to try to, recreate some of these, let's call them features of LSST, as best as possible, so that people aren't surprised by these things, and we can, continue to have these kinds of conversations, perhaps before it's too late. Yeah, so I include the different flux and allow it to be negative, just subtract the whatever flux for each, for each epoch going to be by the median observation. So there will be positive and negative fluxes adjusted by the median epoch.
Yeah. One of the reasons I was wondering, because I've noticed in pan-stars, the star-galaxy separation seems to fail badly for strongly variable objects. Something goes wrong, like your separation doesn't allow for the thing to change by a couple of magnitudes or something. And because then the PSF changes or looks like it changes and stuff. And depending how you do subtraction, I'm guessing you can get confused. And if we have, like, AGN can have flares by 0.4 magnitudes every now and then. And so it might mess up something. In the coad, it'll have a weird composite shape or something. And then it'll fake out the blender and maybe cause other problems. Have you guys thought about that?
Yeah, I would like to learn more about this this pan-stars failure mode.
Yeah, I'm not sure I just noticed that a lot of our O'Leary stars are misclassified as galaxies, and I couldn't find another reason why, but compared to other objects. So, and that's possibly one thing, because when you try and deblend stuff, if your object varied on you by a lot, it screws up the characteristic total PSF shape, because sometimes half the PSF is in the noise and then half time it's well above it. So
right, yeah. And if your coad PSF is a coad of the PSFs and it's weighted by the original weight of each of the input images that goes into the coad, that is not that optimal weighting is not necessarily accurate for your variable. Your variable.
Yeah, exactly. That's what I was thinking. Yep.
And then yeah, it'll look like your source is not a PSF.
Yeah, exactly.
Okay. Yeah, I have not like personally, I have not thought about this scenario, but I will make a note.
So I think we're getting close to the end of the hour we had assigned for, or the 45 minutes we had assigned for discussion, but I don't know if there's any last questions anybody would like to ask. If not, then
I have a last announcement, not a last question, if that's okay, really quickly. So again, for all the speakers today, as well as the speakers from yesterday, thanks for those of you who've already sent me your slides. If you haven't, please do send those along. I will try to collect them and make them available to everyone. That's everything. Thanks.
All right, so if there's nothing else, just want to thank all the speakers. Today's a great number of talks, as well as Jesper for answering all of our questions about the pipeline. So see you tomorrow at 10:30 a.m. Eastern time for the last day of the meeting. Thank you very much.
Thanks.
Thank you.
Thank you. Bye-bye. See you tomorrow.
Bye.
Bye.